Live. I'm live. There we go. Now I'm live. Cool. So, number one, I talked about the SAT, PSAT. I don't know what they're doing for the virtual kids. Like, if you're fully virtual, you can't. Are you gonna come in and? I don't know. You guys aren't fully virtual, but like, if you're fully virtual, do you come in and take the SAT, PSAT? I don't know how that actually works. Regardless, that's how the thing's going. Did you guys hear what's happening at Southern? No. You have a week off in November, correct? Cool. Southern teachers indicated to their administration that there's going to be a certain number of teachers who will have to self-quarantine after that week off. And basically, Stafford schools, I should say, maybe not Southern, but Stafford schools decided, hey, yeah, after that week off, we'll just do 2 weeks virtual for everybody. And the parents are mad. They are so mad. Other school districts in the county have also decided to do that. I think Howell may have decided to do that, but then they rescinded that as well. Shut down completely? Oh, crazy. We'll see what happens. But I know that last week a survey was sent out to Barnegat teachers asking the same question. What are your plans? Personally, as a parent, I think it's kind of irresponsible for someone to be like, yeah, I'm going to a state that I'm going to have to quarantine for 2 weeks when I get back. So peace. No. Well, you have a job to do. Anyway, I'm going to calm down. I'm going to be good. Yeah, I'm speaking as a parent, though, just because my kid's in school, and it's like, come on. But anyway, I know that the surveys are in, and the administration is discussing it right now as we speak. So we'll see what happens. Regardless, my plans continue. Last week, you had a couple things due for me. I'm going to be looking through those things this week. You had the Edulastic assessment. If you didn't get the Edulastic assessment done, make sure you get that thing done. It is now considered a little bit late, but you can still get something for it if you haven't taken it. Same thing with the project. Right now, the project would be considered late if you haven't turned it in. I'm going to begin looking through those this week, and we're going to kind of go from there. I eventually will be making a video in regards to the Edulastic assessment, but I'm not going to be doing that right away because the second that I do that video, I have to close out the chance for everyone to kind of take it. So I'm giving people some extra time. If you haven't taken it, get on the Edulastic assessment. Anyway, as for today, we are going to be jumping into more of quadratic equation and all of its wonderful goodness and all of the aches and pains that come with it. As a side note, there is something on Google Classroom. Let me kind of bring that up right now. There is something quick and easy for you to do on your enrichment day for Google Classroom. It's called Quadratic Check. I just posted it I don't even know. There it is. I posted it like 15 minutes ago. It's super easy. It's super quick. You'll have 3 attempts to get that thing done. But yeah, it's based on what we've done in the past. You'll be able to get that thing done. But like I said, 3 attempts. Make sure you're getting that thing done on your enrichment day. And click off of that. In the meantime, I do have a video to kind of introduce where we're going with this. Because last week, we talked about the quadratic formula. And we talked about the value of what we called the discriminant. The discriminant being b squared minus 4ac. And in our notes for the discriminant, I talked about the types of solutions that we would have if the discriminant was positive or 0 or negative. And if that discriminant was negative, then you were to write down no real solutions. But today, we are going to take that a little bit farther, as I have promised. So I want to introduce a little bit with this video. Now, I'm going to put the volume up a little bit. This guy is going to explain a little bit as to what the heck is going on with what we call imaginary or complex solutions. Make sure my volume is good to go. There we go. And
let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis. So according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power or degree of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting.
this is the coolest thing that I've ever seen displayed in terms of complex numbers. Absolutely the coolest kind of CGI that I've ever seen in a low-budget YouTube video. You're not going to need to know what the complex plane actually looks like. You're not going to need to know how to draw this because no one in their right mind would even try to draw something like that. But just the general idea that I tell you, hey, what are my solutions? And we say no real solutions. And we say no real solutions because this thing does not cross the x-axis. But according to what they call, and we will get into this in the next chapter that we cover in Algebra 2, we're going to cover something known as the fundamental theorem of algebra, which talks about the number of solutions you should be getting from any graph, any polynomial. And according to the fundamental theorem, we should be getting 2 solutions. Well, those 2 solutions don't exist in what we call the real numbers. Those 2 solutions exist in something that is actually known as the complex plane. Let me continue this video.
Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention.
I'm going to skip past this because literally he expects you to read this, but just know that Gauss didn't like the name imaginary, neither do I.
So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral. So from here on, let's let lateral mean imaginary.
I'm going to refer to them as complex. I'm not going to use the word lateral.
To get a better handle on imaginary, lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address them.
Yeah, not next time. Me next time. Mathematicians call things after how they feel about them. Think about it. If I think of the numbers like 1, 2, 3, 4, what do you call those numbers? As a kid, what did you call those numbers? Numbers 1, 2, 3, 4. What? Just numbers, nothing else. You didn't call them the counting numbers, the positive numbers, the natural numbers. That's what they're referred to. Think about those words. Natural, positive. But then we discovered numbers on the other side of the number line. What did you call those? Negative numbers. Now think about that. Negative is for the lack of a better term, a negative word. Negative is equated with bad. We didn't like them, so we called them negative numbers. The words that we use are vitally important, but they also give us a clue as to how people felt about them. You came up with fractions. Fractions were great. Fractions we called rational. Rational numbers. What's the root word? The root word of rational? What is the root word of rational? It's why we call them, that's why we set them up as fractions. What's the first 5 letters of rational? Ratio. We call them ratios. 1 to 2, 2 to 3, fractions. But then we discovered numbers that could not be written as fractions. Numbers like pi and the square root of 2. We could not write them as fractions. There was no conceivable way to do it. So we came up with a name to call them that basically described how we felt. We called them irrational. Irrational numbers. Hey, you're being really irrational today. It's a negative term. Then we discovered numbers that didn't fit any of those categories. We found numbers that didn't fit on the number line whatsoever. We couldn't figure out what to do with them. We figured, they don't exist. So they called them imaginary, which is unfortunate because they exist. They exist. Here's what I want to do. I want to give you some definitions and some basics on what we call complex numbers, unfortunately called imaginary, and I want to show you how they fit into what we've been doing with quadratics. Ladies and gentlemen, if you would, I'm going to need those notebooks out and open. Come on, you. Close that. Open that. There we go. This is so large. Boom. Here we go. Let's see here. Today is the 12th. This is quad formula continued, parentheses, complex numbers. It's quad formula continued. I abbreviated. Parentheses, complex numbers. Zooming in. There we go. So, the square root of -1. Right now, if you were to attempt to take the square root of -1, whether it be on a graphing calculator, the computer, your phone, whatever, if you attempted to take the square root of -1 as is, let me clear that out. Let me zoom in a little bit on my calculator. Watch what my calculator does. If I took the square root of -1, it will give me an error, but I want you to pay attention to the type of error that shows up. Non-real. Non-real. The real numbers, as we have denoted them, the real numbers are your counting numbers, negative numbers, fractions, square roots, typical square roots like the square root of 2, square root of 9, square root of 101, doesn't matter. Pi, things like that are considered real, whereas the square root of -1 got me a non-real, and that sucks. But there is something I can do to my calculator. Watch what I'm about to do here. If you've ever hit mode, if you've ever hit the mode button on the calculator, and of course you have those on your computer, doesn't matter, don't worry about it, just watch what I'm doing. And if you go down here, there's this thing that says real that I'm blinking on right now. Next to it is what we refer to as a complex number. And I'm going to write this whole definition down for you in a little bit. A plus BI. By clicking on that A plus BI, I am telling my calculator, hey, please take into account complex numbers. So now when I go back and do this calculation, look what my calculator says. All of a sudden, it gives me an answer. Now, it may not be an answer that you're happy with, but this is a number that exists. This is a number that exists in our world today. It's just that you guys are not very comfortable with it. The point of me showing you that video was to give you a little bit of the history behind numbers. At one point, people were not happy with negative numbers. If I go to my son today, my first grader son, and I ask him, what is 2 minus 3? He is not going to know what to do. He will put up 2 fingers on his hand, and he will attempt to take away 3. And he can't do it. Because as a first grader, he has no concept or familiarity with what negative numbers are. Now, you guys are kind of in that same boat. See, when you take the square root of a number, it's supposed to work out quite nicely. When you take the square root of 81, you tell me 9. Why do you tell me 9? Why is the square root of 81 equal to 9? Why is that true? It just does it, Mr. Murky. I just type it in my calculator and I hope for the best. But why? Why? I don't know. Let me try another one. I'll write it up here. What's the square root of 144? You know the square root of 144 at the top of your head? It's 12. Why? Because 12 times 12. Square root of 81 is 9 because of 9 times 9. That is why the square roots work. Now, I go to something like the square root of -1. See, the thing is, you can't say that it's 1. You can't say that it's 1, no, because 1 times 1 is not -1. You can't say the answer is -1 because -1 times -1 gives you +1. That can't work either. So for the longest time, the best that we could do was this. We wrote it out as the square root of -1, but we got tired of doing that, so we devised a symbol to take its place. Like pi. You guys know the symbol for pi. You learned it in years past. Instead of writing out 3.1415926535, you would just write pi, and that would be great. Instead of writing out a giant decimal of 0.3 repeating forever, 0.3333333, instead of writing that out, we devised the symbol of a fraction to represent that decimal. So in this case, whenever we see the square root of -1, you will forever replace that square root of -1 with an I. And again, unfortunately, they've been referred to as imaginary, but that does not give you the full story. This is known as a complex number. It's a complex number. Now, for example, I could say the square root of -9. Now, we know what the square root of 9 is, but what about the square root of -9? Let's just see what happens. I can break this thing apart. According to what you learned last year in geometry, I can break this thing apart into the square root of 9 times the square root of -1. We know what the square root of 9 is. We know that the square root of 9 is 3. And based on the definition that I just gave you, the square root of -1 will be an I. So if this becomes a 3 and this becomes an I, it just becomes a 3I. Now, that's something that you may not be comfortable with, but that is how the rules of this thing apply to each other. That's how it applies. That's how it works. I'm going to stick with this example, but I want to show you what it looks like here. This would be the square root of -9. Now, mind you, I've already set my calculator. I've changed the mode in my calculator. Boom, 3I. That's what it spits out. Now, let's go back a little bit here. I want to give you one extra piece of information before I show you how this applies to what we've been doing. I want to show you how this applies to what we've been doing. First and foremost, little extra piece of information that's very important. The calculation of I squared. I squared. Now, I squared, that is, what is that? I squared. Let me just show you something here. I is the square root of -1. And if I is the square root of -1, I can simply replace that I with the square root of -1. But you tell me, what happens when a square and a square root come into contact with each other? What's supposed to happen to a square and a square root when they ram into each other? I don't know, Mr. Morgan. Let's just see what the calculator says. All right, let's just see what the calculator says. Because something happens here. Check this out. I'm going to zoom in on my calculator again. And we're going to talk about the calculation I squared. By the way, for the sake of argument, I'm going to show you something on the bottom of the calculator. You all have this on your calculator. But look, I'm going to move this up a little bit. Look what's above the decimal point written in yellow. Look what's above the decimal point written in yellow. No, on your calculator, on your computer, it might be a different color, but that's okay. It's above the decimal point. It's second decimal point. You can get the calculation of I squared. Look what happens. Chapow. It's just a -1. The reason why that is, is because of the question that I asked before. What happens when a square root and a square come into contact with each other? The answer is they cancel each other out. They cancel each other out. And if a square root and a square cancel each other out, you're just left with the inside. It's -1. Now, how that applies to what we're doing. How that applies to what we're doing is this. Before, I would give you a problem like this, and I would say, solve x squared plus 9 equals 0. I would say solve something like that. And we would go throughout the process of beginning to try and solve that. Now, my first option would be solved by factoring. Move this up a little bit so people could see this a little better on the computer. There we go. I would say, hey, solve this by factoring. Okay, Mr. Markey, I'll solve it by factoring. A times C gets me 9, positive 9. Okay, cool. Because the B value is missing, but the B value was a 0. So I'd be like, A times C gives me 9, and now I got to find 2 magic numbers. I have to find 2 magic numbers that multiply to 9, but add up to 0. Now, notice I'm not writing this on the Elmo screen. I'm writing this in dry erase marker. I'm going to erase in a moment because the stuff that I'm writing right here is nonsensical. Well, could it be 3 times 3? No, it can't be 3 times 3 because 3 plus 3 is 6. Could it be -3 and -3? No, it can't be that because they add up to -6. No such numbers exist. No such numbers exist. It's not factorable. It's not factorable. The Tucker method will not work here. You cannot factor this thing. Okay, fine. Let's do what we did last week. Let's do the quad formula. So I move towards the quad formula. And I decide, okay, let me write it out for myself, which, by the way, if you want a good way of memorizing the quad formula, write it out every time you use it. If you want a good way of memorizing the quad formula, write that thing out every time you use it. A is equal to 1. B is equal to 0. C is equal to 9. Because I'm trying to solve this thing, I got to identify A, B, and C, and I got to shove them into the formula. Let's calculate this separately. You guys remember what that's called? From last week, we gave it a name. Starts with a D, ends with an discriminant. Oh, got it. I know. It's a terrible word. It's a terrible word. It's not a word that people typically remember, but it's important to recognize that you should calculate it separately. It'll make your life easier. Let's see, 0 squared minus 4 times 1 times 9. Holy crap, that gives me what, a negative 36. Ouch. Yes, a negative 36. Because you are going to get no real solutions. However, and let me write this down. This is just an important piece of information that I want to write down on this thing. So, because discriminant is negative, no real solutions. However, there are 2 complex solutions. Let me move this up. People could see it a little bit better on the computer screen. Move this over a little. I'll read it again. Our discriminant was negative 36. I calculated that from 0 squared minus 4 times 1 times 9. Then Okay, well, our discriminant's negative. Based on what we did last week, no real solutions. I agree. There are no real solutions to this problem. But, however, there are two complex solutions. There are two solutions that are in the complex realm, in the unfortunately named imaginary world. But it exists. It's not fake. It exists. So how does one find that? Well, we find that by doing the following. I'm going to go back to my quad formula. My quad formula tells me negative b plus or minus the square root of the discriminant, the whole thing, over 2 times a. I'm still going to use the quad formula. I'm still going to go ahead and actually knock this thing out the way that I typically do. Now, this is going to be the part that people are going to like trip up a little bit at. The fact that they have to simplify this square root. Sometimes the calculator will give you a nice answer. Sometimes the calculator will not. I'm going to have to figure it out like this. Negative 0 is just 0, so it's really just 0. But I still have to deal with plus or minus the square root of 36 times the square root of negative 1, the whole thing over 2. I'm breaking this thing down piece by piece. The negative 0 is not going to do anything because it's being added or subtracted, doesn't matter. But the plus or minus root 36, I can break it up to be the square root of 36, which we're familiar with, and the square root of negative 1, which I have introduced to you as a negative number. The whole thing is being divided by 2. So, square root of 36, this is just plus or minus 6i, the whole thing over 2, which 6 divided by 2 is just 3. So this is plus or minus 3i. Bring this down a little bit. That's a terrible problem. It's a wonderful problem, but it's a terrible problem. This is the way that we're going to have to do these problems. Now, there's multiple ways to get it done, but I'm just showing you one of the more basic ways to get it done. Question for you all. How does one check to make sure that you are correct? How do you normally check math problems to see if you're right? Plug it in. Well, here's the thing. Same thing here. If you want to check to see if you're correct, you got to plug this thing in. You got to plug this thing in and see if you're right. So I'm actually just going to do that separately right here. I'm just going to do that separately right here. Well, if I'm correct, it's supposed to be x squared plus 9 gives me 0. Okay, let's plug in a 3i. If I plug in a 3i squared plus 9, the result should give me a 0. We know what 3 squared is. We know 3 squared is positive 9. You tell me, what is I squared? We wrote this down. What did we determine I squared was supposed to give you? According to your notes. What is I squared? Well, I is a complex number, but what happens when you calculate I squared? What is the result in? Ooh. I'm going to write this separately over here. I squared is actually the square root of negative 1 squared. What did I tell you happens when a square and a square root come into contact? They cancel, leaving you with what? Yeah. See, the interesting thing is, yes, negative 1 is a complex number, but when you square, I'm sorry, not negative 1. I is a complex number. But when you square that complex number, it actually becomes a real number. See, in reality, this calculation right here, 3i, the whole thing squared, actually becomes a -9, which is really messed up. I'm going to show you this on the calculator in a moment. It becomes a -9 because when you square that I, that's what it becomes. So if I do 3i squared, if I'm correct, then when I hit enter, the calculator should say -9. Because when you square that I, that's what it becomes, a -1. So if I did 3i squared plus 9, it works. If I did it again and inserted a negative sign right there, it works. Because when you square that negative, it just becomes positive. It's really messed up to think about. It's really, really messed up to think about. But that's what these things do. You really want to know a messed up calculation? Watch this. I'm going to take a little rabbit trail. Check this out. It's going to take like 30 seconds to explain. E is a number that you will learn eventually when we get to a higher chapter. I think like chapter 7 or something like that. E. You know what pi is. Pi is 3.141596, etc. You know what that number is as well. Crazy. And I just explained to you what I was. The square root of -1 is I. Look at those three numbers. Look at those three numbers. Look how terrible they are. Look how terrible those three numbers are. Now watch this. This is really messed up. E to the I times pi power. Look at this. Look at this junk right here. Look at this messed up junk. Basically, I'm taking 2.718 ... and I'm raising it to the power of 3.14159 ... times I right there. E to the I pi hour. Look how messed up that calculation is. It really is messed up. Watch what happens when I hit enter. That's one of the most beautiful things I've ever seen in my life. Why? I don't know. I mean, I do know, but you won't know for a few years unless you actually deep dive into mathematics, trigonometry, and whatnot. But that's for another day. Let's go back to this. Zooming back out, zooming back out. There we go. Okay. So, one more example of the such, so we can talk about this, and then I have some things that I want to do on a worksheet. One more example right here. X squared plus x plus 1 equals 0. One more example of the such. I'm going to bring this to Desmos in a moment. Would you give that opportunity to write it down? Let's see. Desmos. Love it, some Desmos. Go to your graphing calculator, Desmos. X squared plus x plus 1. There it is. Look at it in all its glory. It has no real solution. No real solution. It does not have an x-intercept that it crosses visually. No zeros, no roots. I guess we're done with this problem. No. Now that we have the quad formula, now that we have complex numbers, we can solve such a problem as this. We can, and it's wonderful. What we can do is this. Microphone. First, you identify the values of A, B, and C, which in this case I purposefully made. Can't see it. I purposefully made 1, 1, and 1. Make sure we have that. Then we need to figure out the value of the discriminant b squared minus 4ac, which in this case, again, I got to throw all those ones in. So it would be 1 squared minus 4 times 1 times 1, which if you did this correctly, would give you the value of -3, which again, no real solution. But there are two complex solutions. Two complex solutions. So I go to my quad formula. All right. -b plus or minus the square root of the discriminant divided by 2 times a, which would be 2 times 1. All right. I can't leave my answer like that. I can't leave my answer like that. I have to deal with that negative. I have to simplify this problem down. I have to try and simplify it down as best as I can. Here's what you have to recognize. Here's the only thing that you have to recognize for the moment. For the moment, what you need to recognize is the fact that that square root of a negative, square root, not cubed root, not fifth root, but a square root. The square root of that negative is going to pop out as an I. Because when you take the square root of -1, it automatically denotes that an I should pop out of that problem. And when that I pops out, that square root will no longer be of a negative number. That square root will be of a positive number. So let's do that. This should become the following. It's a tiny distinction. It is a tiny distinction between a right answer and a wrong answer, but I need you to be able to recognize it. All that happened was I recognized the fact that that -1 was being multiplied by that 3. So I took something like the square root of -3 and I split it up. And I split it up into the square root of 3 and the square root of -1. Well, this square root of -1 just becomes an I. Typically speaking, we put the I in front. We usually put the I in front of the square root in that case. It's a messed up answer. It's a terrible looking answer. It's an answer that really doesn't make any contextual sense at the moment, but it's the answer that we get. It's really messed up. Let me zoom in. Check this junk out here. Check this junk out here. I could do something like x squared plus x plus 1. I could graph that thing out. Chapa! Clearly no real solution. But watch what happens when I try to type this junk in now. Parentheses, -1 plus I square root of 3 divided by 2. Now, I do have my complex numbers turned on so that I should work the way that I hope it will. Chapeau, data type error. Of course it would be a data type error. But what should happen if my dreams would come true? What should the y value be if I'm correct? What does this equation equal on my worksheet at the very top if I'm trying to check my answer? It equals 0. It should equal 0. It should give you 0. Apparently, the calculator is not going to cooperate with me. But let me see if I can force it to work. I believe I can force it to work. -1 plus square root. No, let's do I square root of 3. Boom, boom, divided by 2. Close that. Squared plus parentheses, -1. Let me open up another parenthesis up here. Boom. Open up another parenthesis, -1 plus I square root of 3. Boom, boom, divided by 2. Boom, plus 1. This really messed up calculation, I believe it's going to work. If it gives me a 0, I'm a genius. If it doesn't give me a 0, I'm still a genius, but I'm still trying to figure it out. Look at that. Look at that junk. Yes. Mathematics in all its glory. you have the tools. You can get this thing done. Ladies and gentlemen, I need you to dig into whatever paperwork you have, and I need you to try and find something that I gave you last week. I gave you this worksheet that says practice 4.6 or 4.6 practice. Dig it out if you have it. If you don't, I do have extras, but I want you to dig out what you have first. For those on the computer, this PDF file should be in the stream in your Google Classroom. I believe that I moved it near the top. It's probably going to be after the link to get to this live stream in the first place. Anybody need a copy? All right. That was the word problem practice 4.6. You got one? Okay, I got it. There we go. Now, we worked on a problem or two off of this last week, but I want to do some more. Let's deep dive this thing. Let me pick a problem at random. Now, again, will we get complex solutions? Maybe, maybe not. But the point is that you should recognize what type of answers we are supposed to be getting. Zooming out. I'm picking a number at random here. Let's pick, or not really at random, but whatever. Oh, there's a good one. Number 26. Let's write that down. Off of this worksheet, example number 26. Example number 26 is x squared plus 3x plus 6 equals 0. Now, I could attempt to do the Tucker method, but unfortunately, the Tucker method is not going to work out the way that I hope it will, because if you did a times c, you'd get a 6, and there's no conceivable way to multiply to 6 and add up to 3. So my only option is the quad formula. If I'm doing the quad formula, I'm going to identify A, B, and C so that I can throw them into the appropriate places. 1, 3, and 6. Make sure the equation is equal to 0. Make sure. If it is not equal to 0, then there's going to be an issue. So let's do a b squared minus 4ac, which would get me 3 squared minus 4 times 1 times 6. Oh, this is going to be interesting. 9 minus 24. Oh, let's double check that. Oh, negative 15. Now, if you look at your worksheet, for number 26, they give you 3 parts to complete on the worksheet. They say complete part A, find the value of the discriminant. Boom, there's the value of the discriminant. But then they want to know, describe the number and type of solutions. They want you to describe the number and type of solutions. Now, basically, here's what it comes down to. Last week, you would have said no real solutions. That's still a correct statement. No real solutions. Because the discriminant's negative, it would go underneath the square root, and we can't take the square root of a negative and get a real number. But because of what we're doing today, you could also say 2 complex solutions. Now I'm going to write down both statements. Because this number is negative, this means no real solutions, but 2 complex solutions. The greatest mathematician of the 19th century, his name was Carl Gauss, amazing man, was able to do complex calculations in his head basically by the age of 12. This man came up with what is known as the fundamental theorem of algebra. The fundamental theorem of algebra states that the degree of a polynomial will indicate the number of solutions it will have. Now, there's a few caveats to that whole thing, but the degree of the polynomial that we have is a second degree polynomial, implying there will be two solutions. In this case, the two solutions happen to be what we call complex solutions. So I move ahead with the quadratic formula. Negative b plus or minus the square root of the discriminant. The whole thing is over 2 times a, in this case 2 times 1. I can't do anything with the 2 times 1 because it's just 2, but I can do something with that square root of negative 15. I can break it up. I can break it apart. And you simplify if it allows itself to be. That's all you can do to the problem. That's all that you can do to the problem. It looks like a terrible solution, but that is what it is. It's horrendous, but I love it. All right, let's pick another problem at random. Give me a number from 15 to 29, but not number 26. Give me a number from 15 to 29. Any number you want. 16? Let's do it. All right. Now, this one may or may not give us a real solution. Let's just see what happens. Number 16. X squared equals 3x. This is terrible. What does this problem not do for us that we need to do? Technically, the c is not there. You can't see it. You can't see it. Technically, the c is 0. But what do we have to do to this equation in order to move forward with it? Absolutely. Absolutely. And yes, your c value is 0, which we're going to have to take care of in a little bit. Get it equal to 0. Get it equal to 0. Subtract that 3x over. All right. Now, let's not do factoring right now. We could do factoring right now, which I'm going to show you what you could do in a minute, but let's just do the quad formula. Let's just do the quad formula. Let's just see what happens. A is 1, B is negative 3, and as he said before, C is equal to 0. And we do have to take that into account. Your C value is 0. So I'm going to do a B squared minus 4AC, which gets me negative 3 squared times 4 times 1 times 0, which ultimately negative 3 squared is just positive 9. Now what that tells me, because my discriminant was positive, that means that I'm going to get 2 real solutions. The only way you're going to get a complex solution is if you take the square root of a negative. In this case, real solutions. Awesome. Let's just see what happens. Negative b. Notice how I wrote negative b. Plus or minus the square root of 9. The whole thing is over 2 times a. Again, I just want to emphasize how I wrote the negative b because that's going to play a big role. It's the negative of negative 3, which is positive. 3 plus or minus 3, the whole thing over 2. You're going to get 2 real solutions. You have to do the calculation twice, once with plus and once with minus. You have to do the calculation with 3 plus 3, and then separately with 3 minus 3. Well, 3 plus 3 is 6. 6 divided by 2 is just 3. Oh, happy day. But then you're going to have to do it with 3 minus 3, which gives you 0 over 2, which just gives you a 0. There are two situations in which high school students think they're wrong. They think they're wrong if they get like a messed up decimal or fraction, and they think they're wrong when they get an answer of 0. Sometimes 0 is a solution. It happens. I'm going to show you what this thing looks like on Desmos in a moment. Check this junk out real quick. What's step 1 of the Tucker method? What's step 1 of factoring? 3 letters that we always love to think about. Greatest common factor, GCF. First step. Now, he said there was no C value. I agree. The C value is not there. He said there's no C value, so we don't have to worry about a C value here. But GCF, you can take out an X. And if you took out an X, you're left with this. And if you continue with, well, actually, the factoring is done. It's factored. The Tucker method is complete. Once I take out that X, I don't have a quadratic anymore. I don't have to worry about the Tucker method, but I still have to solve this thing. So I got 2 things being multiplied together to give you 0. All right, let's just set them equal to 0 then. X equals 0 and X minus 3 equals 0. Oh, look, that one's already solved for. Oh, I add 3. I show you this to compare the 2 methods. Sometimes factoring works very nicely. Sometimes it doesn't. If you could have factored this thing, go ahead. You could have factored this thing. But this problem did want you to do the quad formula. Let's do another one. Pick me what numbers were they? They were numbers 15 to 29. Give me a number from 15 to 29. But it can't be 16 and it can't be 26. Give me a number from 15 to 29. Any number. Any random number. Ooh, let's see 17. What's 17 look like? Hold on. Oh, that's a fun one. Nice. Let's do that one. You pick the one that the numbers do not simplify out very nicely, but it's perfect. It is perfect. See, the reason why I'm having you pick random numbers is because it doesn't matter which problem you pick. It doesn't matter. What matters is that we recognize how to use this formula. What matters is that we recognize complex solutions if they happen to show up. Let's do number 17. And then I have one to pick. 9x squared minus 24x plus 16 equals 0. It's already equal to 0. Your A, your B, and your C. It's the same thing every time. It's the same thing every time. Let's just see what happens. I'm going to have to do a B squared minus 4AC. B squared minus 4AC. Let's just let my calculator handle that for a moment. Negative 24 squared minus 4 times 9 times 16. Holy crap! That worked out better than I thought it would. What kind of problem did you just pick? That's great. Getting a discriminant of 0 is like Christmas. How many solutions do you get if you have a discriminant of 0? Looking back at your notes from last week, how many solutions did you get? Say again? Yeah, one real solution. Now, technically, it's what they call a repeated solution. So technically, there's 2 solutions, but we're only counting it as one real solution. That's amazing. Let's keep going. So negative B plus or minus the square root of 0, which is just 0, divided by 2 times A. Oh, look at that junk right there. That looks nice. Well, here's the thing. Square root of 0 is 0. When you add 0 or subtract 0, it does nothing. So it's just 24 divided by 18. Let's simplify that down. 4/3. That is nuts. That is nuts. Ugh. All right. One more problem, and then I'm done for the day. Look at number 30. Did you feel that chill going up your spine? I hope so. Let's look at number 30. Of course, like I said, for those of you in the chat, the PDF of this should be available to you through Google Classroom. I put it into the live stream last week, moved it to the top. For those of you in here, you have a copy of this problem. Let's talk about it. Last problem of the day. The height in feet of an object, t seconds after it was propelled straight up from the ground with an initial velocity of 6 feet per second is modeled by that equation. Let me make a note right here. Modeled by this equation. Okay. At what times will the object be at a height of 56 feet? Now, think of it this way. The object is skyrocketing upwards. It's going up, 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 and then down, 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 down. As the object goes up, it might pass 56 feet. Actually, let me draw you two pictures here. Let me get a little piece of paper to cover this up. I'm going to draw you a couple pictures. Let's cover that up. There we go. Make it a little easier. Watch this. This is really messed up. I want you to visualize this. I want you to visualize this the way that I'm drawing this right here. There are two scenarios that I want to display for you. Here's 56 feet. One scenario is that this object goes up and then down, meaning it passes 56 feet twice. It passes 56 feet once on the way up and once on the way down. That's why they say, at what times will the object be at a height of 56 feet? But there's a second scenario. There is a second scenario that I want you to be aware of. There is also the possibility that this object will go up and then go down. But then what happened to this object? What happened to this object in relation to 56 feet? What happened with this object? What would you say the highest height? Did the highest it reach, did it ever reach 56 feet? See people shaking their head no? Yeah, this object never hit it. See, the thing is, for this one, you would actually get two real solutions. For this one, you would actually get two complex solutions, because in real life, there is no such solution. I don't know which one it is. I have no idea, because I haven't done this problem before. I've never done this problem. Let's do this problem together. Last problem of the day. So I'm looking at this problem. I got to write down some junk. Let's see what happens. Zooming out, zooming out, zooming out, zooming out. Woo, there we go. The calculator is going to do most of this for me. Here's number 30. The height of the object is given by this equation, negative 16t squared plus 60t. They want to know when it will reach 56 feet. Look what I wrote. When will the height reach 56 feet? I don't know. I have to have one side of the equation equal to 0, which is exactly what I'm going to do. I'm going to move everything over to the left. So it becomes 16t squared minus 60t plus 56 equals 0. I'm going to add the 16t squared. I'm going to subtract the 60t from both sides. So I end up with this messed up equation. Now I got to solve it. I'm not going to worry about the Tucker method. I'm going to worry about something else. Oh, blast. All right, hold on. Time out for 1 second. Time for 1 second. I do apologize. Can I tell you why? Do you know why my timing was so messed up today? Look at the clock. Look at the clock. When's the class period supposed to end? 11:05. Supposedly I had 2 minutes left, but no, I don't have 2 minutes left because the power went out. So here's what I'm going to do. You guys, of course, are packing up. That's perfectly fine. I'm going to make a video finishing this problem, and I'm going to post this video for you guys probably sometime tomorrow. So I will finish this problem, but I'll do it online. I'll make a short video about it. Don't forget the quick quadratic check on quizzes, and I'm going to sign off. That's what happens when the